Okay. So X sub n is the initial inventory of period n. So Yn indicates what? Initial inventory plus the order. Okay, so it's the inventory immediately after an order is delivered in period n. Actually, there are some other research telling us that if the lead time is not zero, okay, so then there might be what? Two periods ago there's an order, okay, and then the order arrived, okay, and so on. So this indicates so-called physical inventory on hand. So Xn is initial inventory of period n, and so on. So G of n is the expected holding and shortage cost incurred in period n. So that's almost the same notation as the Mies-Van problem. G of Yn. Okay. So Cn, Xn is the initial inventory. So this is what? The minimal total expected cost for an n-period inventory problems, given the initial inventory at the beginning of the period. You see, that's the beauty of the backward. So n is here, right? So that's an n-period problem. Since this is backward, okay? So capital N then is a capital N period problem. So it looks familiar, okay? So this is expected cost means what? Integration. Don't worry, the same thing, same meaning of it, same meaning. Okay. So originally we introduced this formula. It looks familiar, right? C of n xn is the minimum of the what? Setup cost plus the one period cost problem. Okay. Plus this is so-called cost to go function. Cost to go function. You see, we have n minus 1 period to go, right? N is here, n is 1, right? N minus 1 period to go function plus the period's n's cost, right? So we have this is indicated n minus 1 period to go. Then we have a summation over the future demand. This Z is the future demand. Okay. And this is equivalent to this guy. This guy is equal to this one. You see the maxima of 0 and y, what is Yn? Initial inventory plus the what? This is plus what? Plus the order, right? So you see the 0 and the inventory labels, maxima is what? Holding cost. This is overage, right? So this is what? Underage cost, right? So this one is overage. Okay? Okay? Overage. Okay? This is demand. Z is demand. Yn is inventory label, right? So if Yn is larger than demand, it's positive, right? So maximum between 0 and positive is positive, right? So this is overage. So if this becomes negative, so this turns the value of 0, right? So there's no overage cost. So this is similar to the overage cost. So this is similar to the underage cost. Right? Penalty is underage. We have what? Fewer inventory than demand. Okay? This is demand, this is inventory, right? So then this is positive. If the demand is less than inventory level, so this is negative. Okay? You know what? Actually, I love this kind of expression. This is kind of very straightforward. You know what? Most of you knew the Professor Wen, right? You love this one. You love this kind of notation very much. I don't like this one. But this right, if we write this kind of formulas, it looks what? Fancy, right? 温老师很喜欢写这种，但我就比较喜欢写这个，我比较直觉一点。You see, this is overage, right? This is underage. Okay. Okay, we define what? The end of the period with no value. So which is CZ, the end of the last period, which means the first period, okay, with no value at all. So you see, what is this expression? This is what? The initial inventory of the period N plus the order quantity subtracted by demand. So would be the what? Initial inventory for the next period, right? So this three terms, the value is equivalent to x n minus 1. Now let's rerun it, just like the news vendor problem, period 1 problem. Okay, use this set of notations. Okay, so we define G and the integration as the gamma 1 of y1. Okay, so we take first and second derivative over the gamma 1. We will find the second derivative is positive. So by setting the first order conditions, we will get the what? You see, this look alike, just like the news vendor's result, right? Okay. So because we have the initial inventory, so in news vendor we don't have. Okay. So the order quantity will be revised by deducting the initial inventory, x1. Okay, if the initial inventory is x0, means x1 is 0. Okay, so this is nothing but the news vendor solution. Okay, there's nothing new here. Okay, then we will have the capital S1 is this guy, order up to point. There's an order up to point, capital S1. So then the optimal decision, U is what? U is the amount to order at the beginning of period. That's the only decision variable, right? So U1 condition on the initial inventory X1. If the X1 is less than capital S1, we buy up to capital S1. Yeah. Without settle cost. Okay. The same idea. So how about with settle cost? Again. See? We will find the little s. Okay? Here, the minimum economic scale is the difference between 2s. The same thing with a different notation. Okay. So if settle cost is 0, C1 equal to this 2. Okay. Oftenly we need to check the continuous property for the function. So this is a way to check it. Since the breakpoint may occur at the capital S1, right? We check the limit from the left, and then check the limit from the right, as long as they are equal, okay? So we may say the function is continuous, okay? Okay. This is a way to check the function, whether the function is continuous or not. With this property, certainly C1, because of C1 function has a 2 segment, right? We need to show the possible breakpoint. If the breakpoint, the value are the same, so the function is continuous. Okay, then we take the first derivative, just like the Mies-Bendel without settle cost. Okay. Okay. Then we can prove C1 of X1, just like the C1 in the Mies-Bendel problem, is convex because of the settle cost is 0. Okay, so for period n problem, because we assume if settle cost is 0 by induction, because period 1's result, this one is convex. Okay? Okay, then we assume the result for period n is convex, right? By induction. Assume period n minus 1 result would be with the same pattern as the period 1. Okay? With the same property. Then we can show what? Again, they are all convex. They are all convex. Okay? Then we make sure convex plus convex is convex. How about settle cost is non-zero? We see the convex is this one, right? So this is so-called K convexity. There's a property called convex analysis, right? Actually, I'm going to show there's a so-called K-convex analysis. Okay. So with these tools, SS policy is optimal. With this tool, order up to policy, order up to S is optimal, right? Okay? So with this one, order up to S is optimal. And this one will show SS policy is optimal. You see, this is kind of crazy. You know the author to show this property is not an inventory guy or the OR guy, no. He was a Nobel Prize winner, yeah, in economic area. I believe he showed this one back to 1960. Okay, actually before 1960, everybody was wondering what happened about the inventory problem with the non-zero saddle cost. Since nobody can solve the problem, okay? Then there are the few starting points, try to solve it. One of the most famous one, okay, is what? Using the control chart. Since the demand is stochastic, right? Okay? If we are setting we have the control chart is upper control limit and upper control limit and lower control limit, right? Okay? So we set, for example, capital S here, little s here, okay? Because the demand is fluctuate, okay? How often the curve will outside the limits? Try to use the non-stochastic methodologies like the statistic process to solve the problem. But somehow they all fail. Yeah, they all fail. They all fail. Then this appear. Okay. This appear. This one appear. Okay. Let me tell you, since we don't have much time to finish all of them, since I believe today's content for you is a kind of crazy. Okay, I proved there's 4 lemmas in that in the convex analysis. So next week I'm going to show you the lemmas. Okay. Then let me tell you what happened here. I will be able to understand the content, but it's hard for me can think about the same logic by myself. It's impossible. Yeah. That's impossible. That's impossible. Okay. So actually, we have maybe 3 or 4 slides for dedicate for next week. Yeah. Certainly, I sent you 2 mathematical files, right? One is news vendor, the other one is asset policy. That one I need to show you. Maybe I will take about maybe 1 hour session to show you how to fix that. It's far more complicated than news vendor. Yeah. Okay. Now let me reintroduce the convex analysis. What is the beauty of the convex? Then we will be able to think about the idea in K-convex. Okay, you see the line here. Let's do the same one for convex. For example, this is G of P. Quite often, we use the first and second derivative. Larger than 0. Actually, the most important property for the convex is this one, is not this one. Why is that? You see, the second derivative is positive, means what? The first derivative is increasing. Right? Okay. We have a function f. If f prime larger than 0, we said f is increasing, right? Agree? Right? So you see, because of the second derivative is positive, so the first derivative is increasing. First derivative. You see, what is the first derivative of the function here? Here, in the minimum is 0. Here. Okay. So the slope of these green lines, this is negative, 0, positive, right? Increasing. So the first derivative, the slope is increasing. Slope is increasing. Okay. How to write the slope is increasing? If we have pick up 2 points or 3, take out as A, B, and C. I have G of C subtracted by G of B divided by the difference between C and B. And then G of B subtracted by G of A. B subtracted by A. Which one? Increase. Okay? Any 3 points as long as what? With this relationship. Okay? This one hold. Okay? Right? Increasing, right? Okay? Whenever the A and B, the distance between A and B is small enough, then become a slope, right? Then on the opposite side, we increase the what? The distance between the A and B, and B and C. The properties still hold. Okay, if we move B from here to here, the slope here certainly larger than the slope if we move the B from here to there, right? Because here, the slope here is on the right to the slope here. So this one is larger than that one. So why don't we just increase the distance in between? Become this guy. All the property hold. That's the most important property for convex, okay? Alright, let's see. with the same idea, okay? They pick up the 3 points, A, B, and C. But we all know that impossible to get the property with this guy, right? That's impossible. Do you know? Imaginally, that's all I can say. They show that for that one. You know what? That's the so-called brilliant idea. K is here. This is hope for the K convex function. Okay? See? Okay, make sure I'm correct. Yeah, here, you see? Oh, that's a K. And then finally we have the property, you see? This guy. Okay. You see, capital S is larger than little s, right? Okay? And little s is larger than a number less than little s. Okay, and they show that. I never understand how could they possibly get this idea. Okay, this work. And on the opposite way, you see, what is the convex? K equals to 0. Right? If this is whole for the K convex, okay, K equal to 0. So this is whole for the convex. Okay, so what is a convex? From the idea of K convex, this is also called 0 convex. Means K equal to 0. Actually, the convex is a special case for the K convex. Wow. K convex become a special case. I mean, the convex become a special case. Yeah. That's back to 1960. Yeah. I believe it's 1960. Yeah. 1960. Yeah. Okay. You see. So next week we are starting showing the lemmas. The first one is very easy. A convex function is also 0 convex and K convex. Wow, 2 things. Not only the 0 convex, you see? As long as this holds, right? And because of K is positive, and this is also hold. So convex function is also a K convex function, right? Okay, see you next week.